Good afternoon, everyone, and welcome to today's webinar on compressed air systems, brought to you by Plant Services and Kaeser Compressors, Incorporated. I'm Anna Townsend, Managing Editor of Plant Services, and on behalf of the whole team and our sponsors, I want to thank you for joining us today. The webcast is sponsored by Kaeser, a family-owned company. Kaeser Compressors is one of the world's leading manufacturers and providers of compressed air products and services. Before I introduce our speakers, there are a few housekeeping issues that I'd like to review. On your screen, you should see several primary sections. The upper left corner or audio controls section allows you to adjust the volume of your presentation. Just hover over this section with your cursor until you see the audio control volume, and you can adjust it to your preference. To the right in the largest section is where today's presentation slides will be displayed. Under the slide window, you'll see a chat section where you can chat live with fellow audience members. At the left of the slide window is an Ask a Question box where you can type questions for the presenters anytime during today's webinar. We'll get to as many of those questions as we can during the Q&A session following the presentation. Any questions that don't get answered during our time here today will get passed along to our speakers to answer afterwards. The handout section at the bottom left contains a link to the full set of today's speaker slides, plus a white paper on how to prepare an air demand analysis and an info sheet on compressed air system energy savings. Finally, at the bottom of your screen, you should see icons for additional features. By hovering over each icon, information about the icon will be displayed. If you're having any technical issues or problems, you can type your question or concern into the Ask a Questions box, and our technical engineers will assist you directly. If you need a better view, you can enlarge a section by clicking on the box in the top right corner of the section next to the X. If you accidentally close out a section and you want to get it back, you can click the Restore icon in the far left. It's in the shape of an arrow in a circle. This webinar will be archived, and we encourage you to direct coworkers to the recorded presentation. At the end of the presentation, we'll ask you to complete a very brief survey to give us feedback we need to improve our webinars. Now I'd like to introduce our speakers, Neil Mehltretter and Werner Rauer. We will talk about compressed air system optimization best practices. Neil is engineering manager for Kaeser Compressors, Incorporated. He's an authority on compressed air assessments and has conducted and supervised thousands of industrial compressed air studies, helping users achieve significant energy savings and operational improvements. Werner is a project manager for oil-injected and oil-free screw compressors at Kaeser and is also an active leader in the Compressed Air and Gas Institute. Werner helped develop the widely used CAGI compressor performance data sheets and supported the development and implementation of ISO 11011 and EA4, the new generation of compressed air energy audit standards. Welcome, Neil and Werner, and thanks for presenting today.
Thank you very much, Anna, and welcome everybody to today's webinar about compressed air system optimization. There's a lot of info out there covering pretty much most of the key aspects of a compressed air system. I'm sure you will recognize a lot, if not all, of the terms shown here. But we are not all about using big names and three-letter acronyms here. We don't care if one calls it an analysis or assessment or supply or demand side audit. The key is that we all understand that if we want to talk about a compressed air system, we have to get to know it intimately. You don't do that from the office. You have to at least start with a walkthrough just to see what we're talking about. That walkthrough starts in the compressor room, but it certainly always needs to include a walk down the pipe, so to speak, in order to get the full picture. Questions need to be asked along that trip, so it helps to have a knowledgeable customer to be along the way. A few times you will hear questions about pressure, flow, air quality, and piping. And at the end, we take a closer look at the dirty 30 to see where it all ends, at the point of use, or also called the demand. A measurement plan for the actual assessment study will be made, and some readings will be taken along this journey. Questions about the why will be asked several times. So please don't get mad. We just want to make sure that what we see or hear is what is actually needed. And let's not forget, any walkthrough or assessment is just a snapshot in time. Compressed air systems are a living thing and changing over time. So today, Neil and I will be talking about supply side versus demand side, piping, leaks, and some inappropriate uses, some tools and methods for analyzing. We have a few case studies, and as usual, some tips and tricks on the way. Why is there even a separation between supply and demand? Are there really just supply side or demand side audits being done out there? Well, one could just say that whatever goes into a pipe has to come out somewhere, right? So do we really need this separation? The question, though, is what happens in real time on either side and in between, when the air that is being compressed and provided from the supply side is traveling all the way to the point of use where the air typically exhausts back to the ambient. You can look at this also like a marketplace. If there's a shortage on the supply side, you will certainly suffer the consequences on the demand side. And if there's an abundance of supply, well, waste will take place all over the demand side because air is free, so people will use it. Our take, in 80% of the systems, you only need to about 20% of the available data points, but they need to come from both sides. For the rest, you will have to spend time and money on end just to cover the final 80%. Where to optimize? There are basically just three main areas. Inside the compressor room, covering all the equipment like compressors, piping, tanks, dryers, filters, drains, heating and ventilation, all the way to the point where distribution takes over, like the main piping. And that will lead us to the actual point of use of the compressed air, which may be a piece of equipment, a hand tool, or leakages, for example. There is room for improvement in all areas, even on some brand new systems, as the actual installation may just not be what it was initially designed to be. Now I will pass on to Neil.
Thanks, Werner. Any plant optimization should include what I'll call the big three. So we're talking about leaks, artificial demand, and inappropriate uses. Leaks, self-explanatory, but artificial demand, maybe not so much. This term we coined to express what happens in a compressed air system when operating pressure is higher than necessary. So all your tools are going to consume more compressed air, and likewise, your leaks are going to leak more. So whereas the demand is going to increase, it's not because the tools are requiring more air, it's just a function of increasing that operating pressure. Inappropriate uses, again, seem self-explanatory. However, normally when we're so close to something, we may not see what it is for real. For example, cleaning your air station or cleaning your workstation. Compressed air is available, it's free. Maybe we're using that to clean off our workspace, but it's significantly more costly than sweeping your area or per se using a leaf blower for the same task. So where are all these components of waste hiding? Let's start by asking some basic questions. Are all of your points of use regulated, or are they unregulated? Or maybe there's a mixture, meaning do we have some areas that are using higher pressure air than they really need? Do you have to increase pressure because of low pressure issues at the point of use? So maybe you're compensating. This could be a sign of a distribution issue within your piping network. And we'll see some examples later on. Are there multiple compressors in operation? Maybe one or two might suffice. This could also lead to that higher artificial demand, higher pressures, because we have to cascade multiple compressors in order that they don't load together. And then we see some frequent inappropriate uses, personal cooling, sweeping, as well as using compressed air for air knives. And there's a lot of options to remedy these inappropriate uses, and we'll see some of those later on. We're typically so focused on the task at hand that often leaks in the plant aren't addressed. A 1/4 inch opening at 100 psi is equivalent to about 100 CFM. That's a 25 horsepower compressor. If that leak is leaking 24 hours a day, 7 days a week, and your energy cost is, roughly 10 cents a kilowatt hour, that's almost $20,000 a year. That's a huge waste of money. So what do we do? Well, the fact is that many of your leaks can't be heard or felt. And the best way to find those leaks is through ultrasonic leak detection. There are auditors out there that can walk your plant, identify all of your leaks, tag these leaks, and then provide you with a report describing the estimated flow and cost of each of these leaks. And you can do those things yourselves if you procure the equipment and get some training. The best advice is to fix your largest leaks first. Consider the 80-20 rule. Keep in mind, too, that some pipe materials will corrode over time, and that these materials leak more than non-corrosive materials such as copper or aluminum. If you've got pipe in your facility that can corrode over time, consider making changes to avoid future problems. Remember that the more your system leaks, the more compressed air you'll need now and forever. You can't stress enough, when you find those leaks, fix them. Many companies see the need to document leaks, but years later you visit the same plant and you see the same tags and you hear those very same leaks. Remember, the Department of Energy estimates that 25 to 30% of all compressed air generated for each facility is lost to leaks. That's a significant amount of money spent basically for nothing. Think of it as a lost opportunity cost. Many new vehicles these days, they turn themselves off when they stop to save energy. Shouldn't we be doing the same in an industrial setting? Here's a simple case study. And let's take a look at the demand profile, because that's what we see, and we'll break it down. The average flow right there in the middle of the graphic is about 8,000 CFM. And that's during peak production Monday through Friday. What we see in the non-productive times, off shift or weekend, we're seeing about an average of 3,200 CFM. And that's where we have that 8-point star graphic calling out 40%. That's 40% of your 8,000. That's a really high number. And when the system's running 24/7, that's going to translate to $500,000 per year for this particular facility. That's over half the overall energy cost of this particular system. But that's not all. Typically, the bulk of these non-productive periods is going to be associated with your leakages. In order to feed those leaks, you need compressors. And that means more maintenance costs associated with your system, higher capital spend to replace that system when you need to, and you're always going to need to include those leaks when you size your next system. That means you're overspending for the lifetime of your equipment. Besides finding and fixing these leaks, what else can we do? Well, pipe material should be a major consideration in leak reduction. A non-corrosive choice can go a long way to reducing potential leakage. There are several other design parameters that are going to help you optimize your compressed air system when it comes to piping. I like to think about piping like I think about infrastructure. If I'm sitting in traffic, I typically think, man, this is the worst road design possible. The timing of these lights are terrible. I'm still sitting here. But if you're moving freely, it's the best road design ever. Or maybe it isn't, but you don't even think about it. It's the same consideration for your compressed air piping. Only the compressed air doesn't get enough time to think. It's already moving. So you have to think for it, and you need to design that into your system. So here's some tips and tricks regarding piping in general. In the compressor room, you want to maintain the lowest pressure drop possible while you're minimizing overall velocity. And that's going to go a long way to keeping your compressed air effective. High pressure drop is going to be costly. For every 2 psi increase in pressure, it's going to cost you 1% in energy. The higher the velocity in the pipe, the less effective is your air treatment, so your dryers and filters. Severely high velocity can damage that equipment. Either way, that could mean contamination downstream at the point of use, affecting production, which is even more expensive. Take your drops from the top or the side, that's the best practice. If you make your drops from the bottom of the pipe, that could allow condensate to flow from one location to another, which is what we want to avoid. If your velocity is too high, taking your drops from the side or the top isn't going to matter because the water is going to find its way to the lowest point anyway. Lastly, support the pipe. There are very significant forces every time a compressor loads or demand surge at the point of use. If the pipe isn't supported properly, you can have significant movement of that pipe, which can result in catastrophic failure. So make sure your pipe is supported properly. In the distribution piping, avoid any and all restrictions. Pipe runs should be straight and simple. Avoid unnecessary elbows and long runs of small diameter pipe and or hose. Small hoses, like you can see in the picture at right, they can really increase your pressure drop, resulting in overcompensation back in your compressor room. Keep in mind, too, that point-of-use storage can be a huge success at keeping the demands from adversely affecting your supply or one demand to another. In this pressure profile example, the compressor is actually short cycling. If we measured pressure only at the compressor, we would see a 10 psi swing between load and unload. By measuring farther out in the system, we would find that the 10 psi swing at the compressor is being driven by a 1 psi change in the system. So that's that blue block we've highlighted there at the bottom right. By looking only at the cycle times and without the benefit of good notes that describe the system, one might tell the customer that, hey, you need to add some storage in the compressor room. But what the customer really needs is more than a 1 psi control range down there at the point of use. Looking at this chart a little further, you can see that the actual point of use pressure stays very close to 80 psi. And that's that blue bar that we've highlighted again on that bottom right. It doesn't really change much when the demand is less than the full capacity of the compressor. If the demand equals the full capacity, then the point of use pressure is somewhere between about 70 and 80 pounds. Ask the customer if this is an acceptable pressure range. If 70 psi is acceptable, we could look at reducing the drop connections, and that's the bar that we show in white. We can reduce that from 15 pounds to 5 pounds. That's going to be a big savings. And if we can do that, we can drop the load point from 100 pounds to 90 pounds, further saving energy. This second profile shows the compressor with a 20-pound control range. And then the system is seeing a 10-pound swing in pressure. Also note that when the demand is less than the compressor's capacity, the end-use pressure fluctuates between 80 pounds and 90 pounds. And again, that's that blue bar now that we've highlighted actually in red. The 10 pounds is what we removed from the drop connection, and that went right to the point of use. By changing that drop connection, we stopped the compressor from short cycling, which improves the reliability of the compressor and reduces maintenance costs. But while we've reduced the operating pressure, which is reducing energy, we're also having a longer unload time, which allows the separator to blow down and the compressor to reach its true unloaded power. So all good things. On the negative side, we've increased the customer's system pressure and increased that artificial demand. So the next step would be to drop the pressure in the compressor room either via dropping the load on load set points again, or perhaps adding a flow controller to reduce the system pressure back to the lowest acceptable level down there at the point of use. Here's a different look at supply versus demand. Remember that the demand typically, we would say, starts after the last dry tank in the compressor area, so where the distribution starts. And the supply is typically from the dry tanks back to the compressor. For many operations that are stable, don't have much fluctuations in demand, storage in the compressor room is perhaps of highest importance to ensure proper operation of your equipment. With the demands that are high and intermittent, point of use storage becomes just as important. Compressor room storage is vital to ensure that your compressors don't short cycle. With sufficient storage and pressure differential, there is also the possibility to limit the number of compressors that load for any given event. This can limit your electrical demand charge, providing significant energy savings. So more on this later when Werner talks. That being said, adding storage volume in the compressor room to ride out high demand events may not be feasible. Remember that you're going to have a limited pressure differential in the compressor room. For high demand events, point of use storage should be considered because that's going to improve the speed, thrust, or torque for specific applications, as well as protect critical users from pressure changes in the network and protect the supply side or other demands from those same high demand events, especially when metering devices are used at those points of use. Here's that first supply and demand graphic that we showed you. For an ideal breakdown of operating pressures, these are going to be considered normal or optimized. If we have a 125 psi design compressor at the discharge, you typically have a regulation range of 10. So we're going to be seeing about 115 psi in that wet tank right after the compressor. Dryer filter, we would assume probably worst case scenario 8 pounds of drop. So now we're going to be at 107 right there where supply meets demand. If the piping is designed well, we would see maybe a 1.5 psi drop in the distribution network. And if we had 1.5 psi drop in the connections, that's only 3 pounds. So we'd be seeing about 104 psi at those consumers. In the real world, we're talking about up to a 10 psi drop in the main header piping and up to 30 psi in those last point of use connections. Werner mentioned that dirty 30. So if we add those two together, that's another 40 pounds. So instead of 104 psi, we'd be more like 70 psi at the point of use. So things that you want to consider in your design. Now I'll hand it back off to Werner.
Thank you, Neil. And here are goals of an assessment. Pretty long list. So let's start with evaluation of your system design. Measure power and flow along with the pressure profile, as Neil just talked about. Analyze response to demand, meaning the system responses to demand. Determine the leak rate, and the leak rate could be different during operation of certain areas. Maybe some of them get shut down, so this has to be a long-term observation. Evaluate storage and controls. Neil just talked about this as well. Identify inappropriate uses. That could be a major savings right there. Evaluate air treatment selection. Sometimes we are using desiccant dryers where refrigerated dryers would be absolutely sufficient. And of course, bottom line, improve the specific power kW per 100 CFM or the cost for getting your compressed air. So the key here is that you need to collect enough data on both sides, supply and demand, to establish the dynamics of the system. So what are some typical findings? Pressure, always a main topic. People saying it has always been that way. The tool works better with higher pressure. So typically we find that this is the number one topic. Leaks, of course, yes. We find leak rates between 10, which is super good, and 70, and sometimes even a little bit more percent. This is ridiculous, but it is out there. About 20% of the leaks typically make 80% of the waste, so we need to focus on those. There is water downstream, opening up some valves, bottoms, etc., drains. Then you need to talk about drains, dryers, and valves, for example, bypasses around dryers, which have not been closed. Multiple compressors in the system, maybe even spread around all around a building or various buildings with no common or master control. Neil already went through some of the details on the piping. There's always talk about piping. We have seen up to 3 identical filters in a row. And the response is just in case. We want to be safe. Incorrect sequence of treatment. Yes, I have to admit, people out there, the compressed air experts, they're installing the system. Nobody really is watching out, and suddenly the sequence of the filters are out of order, and you're having trouble. So this is something that is another typical finding. And as I mentioned just earlier, using desiccant dryers plant-wide, where most point of use only need refrigerated air drying, that's a much less expensive way of drying here. Too small an air receiver, no matter where, or the lack of storage in general is one of the most common findings. And then the air is free and clean attitude. So we will find many homemade solutions for cleaning, cooling, and transportation applications. There is a need in most of them for air-saving devices that are being offered nowadays. And now back to Neil.
Thanks, Werner. You know, Werner and I do a good bit of training, and while I really enjoy the sound of his voice, the reason we do so many is to stress the importance of understanding compressed air and your compressed air system, primarily because it's expensive. Expensive to purchase, to maintain, and operate. Even though we stress flexibility within your compressed air system, typically means multiple compressors, dryers, and so on, not just one large piece of equipment, even those systems can run inefficiently if not properly sized and or controlled. In order to understand your system, you need to understand your demand profile, your flow profile, like we looked at a little bit ago, as well as your pressure profile. And again, we showed one of those too. The best way to get this information is to invest in system monitoring and data collection. Better yet, a master controller that can operate your equipment efficiently as well as collect historical data. Before making changes, data log the system. Understand how well or how poorly your system's operating today. Identify those inefficiencies and make adjustments, whether it be adding a master controller, upsizing your pipe, or doing general maintenance. Making changes incrementally allows you to verify those improvements. As with most things, there's a balance you're trying to strike. Stable operating performance with a reduction in energy costs compared with those costs of improvement. Now back to Werner.
All right, thanks, Neil. So inappropriate uses, I think we mentioned a few, would be any time you're using a compressed air when you could use an alternate means to achieve the same effect at a much lower overall cost. Or lower environmental impact like noise or smell or for safety reasons. We find those to be around 5 to 10% of the demand is actually used for inappropriate uses. There may be some more with some very creative people, but this is roughly the average there. For example, this personal cooling has been mentioned. We have seen people that have a copper pipe underneath of their desk and with some holes in it. And as we all know, when you expand compressed air, it has a super nice cooling effect. However, it's very, very expensive for a cooling method. So at least nowadays, OSHA-approved blow nozzles, when we're looking at the picture here on the left here, cleaning effect. So these OSHA-approved blow nozzles are required to prevent some of the dangers. But there still are very dangerous ways to use compressed air when horsing around, so education of your personnel is critical there. Other inappropriate uses would be sweeping the floor, air knives that are used for blowing something off or drying purposes. Some use compressed air for vacuum applications. Those may be better served with specific tools like engineered nozzles, blowers, or vacuum pumps. Most of the compressed air demands shown here are straightforward: painting, air tools, caulking, stapling. It's a manual tool or device that has a manufacturer's rating for pressure, flow, and air quality, so it's pretty easy to identify those during your walkthrough. What makes them targets are the way they're being used, with mostly flexible hose lines that come with the fittings, which are small, the filters, and the regulators. And sometimes you will actually see as well. Oh, I forgot. When we're talking about these tools, the usage factor, when they're all syncing up, or sometimes you see that they're no longer using them. They have all these buffers in an automotive shop that used to be pneumatic, and when you go there the next time, it's all electric. So that would be just one example where they actually moved away from the compressed air. Some uses are not so straightforward. Just looking at those three applications here, it will not tell you its full story. Observing them in operation might give you a hint. Measuring pressure and flow in short time intervals will actually tell you. Watch out again for these tiny hose lines feeding those applications or machines. Case in point here is the use of hard piping with full bore valves on the left versus the hose lines with the small IDs and barb fitting on the right. However, you will notice the point of use refrigerated air dryer, that's the blue box on the right side picture, along with the storage tank and filters. You've got to take a closer look here, or may have to find out more about this specific or special design on the right and include into your air study. Point of use receivers, those tanks, indicate a possible short-term and high flow application. Here, we are looking at two different pressure gauges in action. The point of use on the left, which is a filling machine for some whiskey, I believe, with a close-up in the middle, so that's where you see the tiny rinky-dink pressure gauge, and the larger one on the storage tank or receiver tank on the right. So this is what you can find, and you want to observe during your simple walkthrough. The important things to note: high and low values on either one, and the timing. Look for any rapid changes, where they are located within the system, and know their limitations in terms of accuracy, 2 versus 4 inch gauges, and the fact that probably none of them are calibrated at all. So here we have an example of an aluminum wheel manufacturer. They did a simple air study. Yes, it was a supply side review or study only, which resulted in the recommendation of adding a larger baseload compressor based on the average max and min flows and pressures that were measured inside the compressor room. The survey was done due to low pressure complaints from the shop floor. We did the walkthrough of the plant. Yes, 2 200 horsepower compressors, a dryer, filters, and we also found in the plant 6 aluminum casting machines with homemade copper pipe nozzles for blow-off and cooling. Also an X-ray machine to check the castings and some minor other uses, and we verified the low pressure condition at times. The people who were complaining the most was actually the X-ray machines. So during that walkthrough, just listening to the processes and observing the installed gauges, they indicated frequent high demand events, loud noises all over the place, exhaust noises. What goes into the pipe will have to go somewhere. It's either used, wasted, or stored. To find out the details about the dynamics and the true problems of the system, a study was done using various sensors throughout the plant, data loggers with short time measurement intervals. So, about this, the results on this study, it was noticeable even when you walk through there, but it clearly showed that syncing up of the wheel molding machines created a large difference in temporary flow, anywhere from 400 to more than 2,000 CFM. Same machines, same system, 400 to 2,000 CFM. Average was still around 900 to 1,200. This is what the initial survey kind of showed. On top of that, the dryer was overloaded during those low pressure, high flow times. At the time, they had only one wet tank, and that just pulled that wet air through the dryer in way too fast. It was confirmed, only the X-ray machine needed the 110 higher pressure. Let's come to the recommendations and or solutions. So a new dry storage tank was added along with a flow controller to create actual storage, and that allowed us to take the higher pressure of that storage tank to feed the X-ray machine that so needed it. Another dryer was added for reliability purposes only. The customer decided to install engineered nozzles that can reduce compressed air demand by 25 to even more than 40%. So since it has been requested numerous times, I will mention X-Air. EX-Air is just one company that offers a number of products which reduce air demand. We have recommended them many times, as well as the CDI flow meters that we are actually using ourselves. So at the end, the customer did not have to install a larger baseload compressor, but enjoyed the benefits of the storage and reduced demand to actually keep one compressor off and therefore create a backup with this second unit. The plan was to reduce the now much lower system pressure, which was used for the rest of the plant, to even more within a few weeks to find the actual low point when people start complaining again. Based on our experience, this is just one of the more rare plants that do require dedicated storage for large but short-lived peak demands. This is not on every single plant, rather rare. On a side note, this happened years ago, and we used this application as proof that we, Kaeser, needed to invest into high-speed data acquisition tools, along with justification for more sensors, pressure, flow, pressure dew point, and kW meters. And you might realize by now that detailed system analysis requires substantial resources in time and money. Now I'll get back to Neil.
Werner had a great case study there where the demands were pretty frequent. You could see that in one of the graphics. But what about demands that have pretty long stretches in between? Here's a profile for a filter cleaning operation. Every 4 hours, there's a burst of demand, almost 2,000. And this demand lasts for a very short period of time, only 60 seconds. The other thing is that the pressure requirement is not to drop below 72.5 psi during the event. This flow, 1,750 CFM, is upwards of a 450 horsepower compressor. That's a lot of air, but again, not for a very long time. You know, likely the plant that we're talking about this demand is in is going to have a lot bigger demands or more demands, but if we just break down this particular requirement, then maybe we can see how it could play out. As an option, if we use only a small 3 horsepower compressor to fill a relatively large storage receiver, that 2,500 gallons, that could work. Or we could use a 450 horsepower compressor. Both would feed the demand. The key to size any event like this is to know that required flow, required pressure, the event duration, and the amount of time to refill that storage receiver. In this particular case, either the 3 horsepower with the storage or that 450 horsepower compressor could meet that 1,750 CFM demand event. However, keep in mind the utilization of either compressor. With the 3 horsepower compressor, we'd have a pretty high utilization rate. It's going to run fully loaded for almost 2.5 hours to fill that 2,500 gallon tank. On the other hand, we'd have a very low utilization with that 450 horsepower compressor. It's only going to load 1 minute out of every 4 hours. Now, of course, there's probably going to be other demands if you're putting that 450 CFM compressor in the main compressor room, but if it's just to feed this one big event, it's going to be costly. This type of operation is going to lead to service-related issues on that big 450 horsepower compressor and likely premature failure of major components. Not to mention the capital cost to purchase a 3 horsepower compressor and a 2,500 gallon receiver is going to be only 20% of the cost of a 450 horsepower compressor. So the whole point here is evaluate your point of use demands before purchasing large equipment. Now back to Werner.
All right. This one here shows an example on a larger scale. We are looking at 3 manufacturing areas like interconnected buildings with an existing decentralized compressor system. Those are the gray boxes, top left, bottom right, and top right. Looking at the demands, with doing the study in these various areas, it was determined that it would make more sense to add the 2 new 125 horsepower compressors, those are the yellow boxes in the middle, along with some storage in the center area rather than inside the main compressor room on the top right. So instead of doing a huge piping job to distribute all the flow, the new one, the supply, we produce a minimum supply for each site. And then the remaining demand is satisfied via the existing piping system from the centralized compressor station that controls all of it. Using fiber optics nowadays, these distances to connect sensors and controls and the compressors from a centralized control systems are no longer a problem. So the data available at the new master controller they purchased represents the entire system. And back to Neil.
We've covered a lot of ground today, and when optimizing your station, you want to strive to stabilize system pressure. So take a look at the graphic at the top right. Pressure in the compressor header is pretty stable. Maybe hard to see, it's a small graphic, we fit a lot on this one slide, but that's a line that pretty much goes straight across at about 120 psi. If you look, you see a lot of different pressures down there with different colors. I like a lot of color, so there you go. But you see some of those pressures drop down to about 60 pounds. These pressures were all put out in different areas of the facility, and so this is what users are actually seeing as the demands hit. But the interesting thing is the compressor room doesn't see any of that. So what we've got here is a distribution and possibly a point of use piping issue. Probably the system grew and we added more users. We just can't get the supply out to the demand. So these are the kind of things you want to be looking for when you're doing your system assessments or talking to your compressed air experts about the data. Again, in summary here, higher pressures are going to equal higher demands. Remember that artificial demand we talked about. And that also is going to mean higher leak rates and higher energy costs. try operating your compressors at the lowest possible pressure. That's not only going to save you energy, but it's also going to improve system reliability. Remember that pressure profile graphic that we showed you? Storage is not only going to provide you with better compressor operation, but could also provide you with better operation down there at the point of use. Remember that location of storage does matter. And if you have high demand events, addressing these individually will go a long way to optimizing your station. All right, Werner.
All right, as to the action plan. Well, just, hang on, I need to forward here, I guess. Sorry. So as to the action plan, just do it. Whatever you want to call it, get to know your compressed air system. It is certainly helpful to have a compressed air expert to assist, to provide the facts, recommendations about your system, to look into options about your end users, to identify and eliminate improper uses, maybe even providing the equipment for and to do the analysis. There is a lot of information out there about leak detection and management. So build a team within your organization to motivate and educate your personnel. Get the help along the way from organizations and companies that provide training on compressed air issues. But at the end, you really need to get into constantly monitoring your changing system. It's not just a one-time fix here. Nowadays, this is easier than ever before. The costs have gone down for the sensors, and actually most modern system controllers allow for adding and providing all your monitoring and statistical needs. Training and education must raise the awareness of compressed air costs in your company, the opportunities to lower the air pressure and improve system performance. Monitoring compressed air system performance provides the necessary management information to keep the air system operating efficiently and reliability. Modern system controllers can do that for you. Speaking of those experts, the Compressed Air and Gas Institute, CAGI, has a program that provides certification for compressed air system specialists. The training is available for this program, for example, level 1 and 2 of the Compressed Air Challenge Group. But on the CAGI website, you see those two types of certificates. You need to be a specialist first, then you can become an assessor. There are currently like 100 system specialists that understand compressed air systems and are certified. About 50 people are interested to become an assessor, but that program is still in the beginning, and with the COVID-19 putting a little bit of a damper on the actual testing, but it sure will come. So at last but not least, here are some links to get further information. I highly recommend our U.S. educational resource website at the bottom right there. That is a one-stop shop for updated information. We also, as Anna said, mentioned some downloads beside the webinar slides for you here today. So now I will pass it back to Anna for maybe take some questions.
Great, thanks guys. Yes, now is time for our question and answer period. Just a reminder, if you haven't done so already, you can type questions into the Ask a Question box at the bottom. Okay, first question. How do I know if I'm experiencing high demand events?
Werner, how about I start this one and then you can add your 2 cents, yeah?
Okay.
So, typically you can see that in a multitude of ways. You could see that as maybe a short cycling in the compressor room. You could also see it as when this event happens, you can't run the rest of your equipment in the facility. All the air is going to that particular point, and maybe not all the air, but you're experiencing pressure drop in neighboring areas. And, when you talk to the facility, you say, well, what's your minimum pressure? Okay, well, 80, 82 PSI is really what we can live on. But when we run this particular piece of equipment, I can't run the other pieces of equipment because pressure drop's too low. So those are probably 2 good examples. Werner, you want to add to that?
Well, like you saw earlier, just sometimes walking through there and listening, because most of the air gets exhausted. That actually can give you, with the repetitiveness and sometimes the intensity, that can also give you a little bit of a high demand event experience.
Okay. What is a typical range of required equipment velocity?
That would be you, Meister.
Yeah, sure. It's a really good question. If we're talking about required point-of-use equipment, then we'd really have to figure it out with the vendors themselves. Typically, they're going to stipulate what those values are going to be. For your compressor piping, to get to those points, in the compressor room, we typically say 15 feet per second. In the distribution network, we typically say 30 feet per second. And then at the point of use, 45 feet per second. So, that may differ. Many points of use, like Werner showed in some of our graphics there or pictures, they have additional filtration. They have point of use storage. They may have regulation as well. They might have a regulator or an FRL filter, a regulator and lubricator. So, those are the things that you want to look at and decide on. We have that question a lot too for filtration. Your filter's rated for, let's say, 500 CFM, but it's a 1.5-inch connection. You recommend the network piping to be 2-inch. Why do you neck down? And so, some of that has to do with impingement and making sure that we have the necessary pressure drop across whatever device it is so we can get enough contact. And that's probably the same thing that a point of use would have as well. Good question.
Okay, next question. Every day at shift change, all my compressors come online and pressure drops. What should I do?
Well, let me start here. A walk through the plant may help see or hear things. You mentioned shift changes, so typically what we notice there, we have Geico here, and that was quite obvious there. They do in the mailroom, they use compressed air. Every time they change the shift, right there in that time period, the demand was ridiculous. And yes, the pressure dropped. So what were these people doing? They cleaned their desk, they cleaned the floor, they cleaned the machinery, so the fresh people who came for the next shift had a nice place to start. So that's just one of the experiences that is actually real and probably more widespread.
Okay, next question. In order to initiate an audit, is there a standard template or questionnaire that you can share? How do you support this initiative?
Yeah.
Yeah, it's a great question. There are questionnaires out there. Typically what they're going to do is they're going to allow the user or the auditor to collate all the information that they can from the compressor station. So again, supply side, what are the compressors? What are the age? What are the control types? What is the load-unload pressures of those? What is the modulation pressure? Or if it's a VFD, what's the target? Is there a master? Storage volumes, pipe sizes, etc. So there are some that are out there. Obviously, we use one. I believe there's some other ones out there that are just non-manufacturing, if you would. But it's a great way for you to understand and go through checklists of, does this apply? Does that apply? We have a nice set of questions on our air auditing brochure that just says, hey, do you have these particular problems in your plant? So it's a great way for you to get a feel for what's going on. This is, let's say, a first time that I've had a customer come to me and ask for a questionnaire. Normally we go to them and say, okay, let's fill these things out. So good question. Look forward to working with you on that.
Yeah, and let me just add that over the years or decades I have been with this thing, it started out with a one-pager, and now the Excel sheet, I would say, is probably more like 8 sheets or something like that. So yeah, we do use quite an extensive questionnaire for these kind of walkthroughs and customer visits.
Okay, next question. Any comments on the heat of compression air dryers, and are they worth the expense to install?
Okay, so let me start with that one. That is as Neil would say, good question. Not so easy to respond there. We do have, for example, our dry running or all three machines. They do come with a optional heat of compression dryer that's actually built into the package. So there, in terms of whether it is feasible, you have to do a study. In terms of where you are. Sometimes the machine has like the same size dryer and different flows. So an analysis has to be done or calculation between power costs because the heat of compression dryer does not use pretty much no use of energy there whatsoever except for a tiny motor and maybe a blower. When you comes, there's like some webinars about this out there as well. So I don't want to get into too much detail, but this is a challenge that should be answered by looking at the individual installation or requirement or requests and demands. And also, where do you get that heat of compression from? Does it have to be piped far away? Is it integrated to the package? And so it's not just the cost of the dryer, but you may also have to consider, or you should consider also the installation cost of that particular dryer.
Okay. I think we have time at least for one more. What is the acceptable pressure drop in piping systems?
Yeah, so it all depends on what you're willing to accept. The compressed air challenge comes out and says that the recommendation is 10%. So from whatever your operating pressure is in the compressor room to the point of use, before you start taking that demand is 10%. So let's say if we had a 100 psi operating system, 10% of that's 10 pounds. But when you consider that rule of thumb, for every 2 psi is a 1% increase or decrease in energy, that 10 psi is going to be 5% of your energy cost. So, you want to minimize that as much as possible. And what happens is systems grow over time as well. So from my perspective, one of the examples we gave from an optimized system earlier was 1.5 pounds in the distribution network and 1.5 pounds in the point of use. So that comes out to 3 psi total. That's a little bit lower in percentage-wise because that was a 125 psi system. But, the lower you can go, the better off you're going to be, and it's a cost benefit. If I say I want to go with a 2-inch piping system, well, let me see what the quote is for a 3-inch piping system. That maybe that's $10,000 more, but that's money you're not going to have to spend later as you expand. So things that you need to look at. So I'd say 10% would be I would say the maximum I would be happy to go with, but lower 3% would probably be a really good choice.
Okay, that's about all the time we have for questions today. I'd like to thank our sponsor, Kaeser Compressors Incorporated, all of you that joined us today, and of course our speakers, Neil Mehltretter and Werner Rauer. This webinar has been recorded and will be available shortly for on-demand viewing. You're also encouraged to visit plantservices.com to gain access to even more tools and resources aimed at helping you achieve success. The full set of speaker slides for today's presentation will remain available for on-demand viewing in the handouts area, along with the white paper on how to perform an air demand analysis and the info sheet on compressed air system energy savings. Did you enjoy today's presentation? We hope so. Please let us know your thoughts by answering our brief survey. This will appear on your screen shortly. Your candid answers are not only appreciated, they helped us craft better events in the future. Thank you for your attendance and have a great day.